Hey there, welcome back to the Game Dev Engineer Super Duper Study Sheet. Today we're going to be talking about multi-threading. So multi-threading is something I learned in college and then haven't really thought about since. And then I got an interview which was completely about multi-threading. That's all they wanted to talk about, and I failed it very badly. So here is the review sheet that would have helped me pass. And there's basically just a bunch of terms we're going to talk about today. Atomic types, mutexes, condition variables, and semaphores. But just in general, the idea is that we're working on these systems that have, multiple processors. So, by virtue of that, you're going to want to split up your work. But also, these multiple processors can have different threads at the same time. And so if you could split up your work or parallelize your work, it often makes sense to. However, obviously, there's problems when two things can edit something at the same time. You can have like a race condition. Atomic types are special in that they specifically only allow one thread to read the value while another thread writes. So atomic types are really great for basically allowing you to not have to worry about somebody editing something while you're writing it. Very useful for when you're doing like int plus plus and you don't want somebody to come in there while you're moving things around on the stack or heap. Also interesting is that you can have lock-free atomic types. You don't necessarily need a lock in order to have a atomic type, and we'll talk about that later on with the atomicity section. Okay, so if you want to check if an atomic type has a lock-free implementation, you can check with the isLockFree method. Java calls them synchronized sections. C++ calls them critical sections. The main idea here is what's a section that you don't want two threads working on at the same time. In general, here's the paradigm. You want to wait on some sort of mutex, do the critical section, and then signal with the mutex once you're done. So what is a mutex? Well, mutex is it's a combined word. It means mutual exclusion object, and it synchronizes access to a resource. So it's pretty common that you'll ask, like, they'll say, like, oh, can a mutex be used as a semaphore? Are they the same thing? We'll talk about semaphores in a second, but it's important to know that they're not. A semaphore is sort of like more than a mutex, and so you can use a semaphore as a mutex, but the reverse is not true. You can't use a mutex as a semaphore. And now a mutex can be signaled only by the thread that called the wait function. Recursive mutexes can be locked more than one times, and they just must be unlocked that many times as well. If a thread tries to lock a non-recursive mutex it already owns, that's a deadlock. Pretty often you'll use lock guards, which will tie they will acquire the mutex on construction, and then when the destructor is called for them, they will let go of the mutex. So that is it's a nice way for you to handle locks with using object-oriented principles of object lifetime. An interesting thing is called the spin lock, and so the spin lock mutex will auto try again when it's asked to wait. And then finally, you might want to have a unique lock or a shared lock. And so a unique lock is for exclusive ownership of mutexes, where shared lock is for shared ownership. And so here is just an example where we declare a unique lock. Is that right? Sorry. We declare a unique lock that takes in a mutex called locker. Then we lock locker, and then we unlock locker. So here's just an example of what that code looks like. Okay, so now let's talk about condition variables. So a condition variable is an event-based checking paradigm to replace busy waiting. So the idea here is that if you have one resource that's being used, rather than spinning in a while loop, waiting for that resource to be unused, you can just wait and later be informed when it's time to go. So this is like a big paradigm in computer science overall, which is the concept of polling, which is constantly checking, hey, are you ready? Are you ready? Are you ready? And having event-driven programming where you say, hey, let me know when you're ready, and then you can go do something else, and then they'll say, hey, I'm ready now. So those are two different approaches that are often used in different areas of CS. Okay, so the condition variable is at its core, a synchronization primitive that can be used to block a thread or multiple threads at the same time until another thread both modifies the shared variable, the condition, and notifies the condition. So this is where our mutexes come into play. So basically, at the beginning of a if you want to modify a condition variable, you're going to first acquire the mutex, which represents sort of the lock of the critical section. Then you're going to want to perform the modification while you're still holding the lock, and then execute a notify or notify all on the std condition variable. And so you can actually, so you let go of the lock before you do the notify. You don't need it at that point. Okay, so notify one or notify all notifies one or all waiting threads. And then the default condition variable requires a unique lock. A CV any can be used with any lockable object. And then people always talk about this. It's pretty important for condition variables, but there's a concept called spurious wake-ups. So we talked about an event-driven paradigm where you would say, hey, let me know when you're ready. However, there is a pretty common optimization that is used in implementing these under the hood, which causes them to sometimes say, hey, I'm ready, even if they're not. And so that's called the spurious wake-up, and it is definitely worth the performance advantages of having this. So people often have this in their system. And so what you need to do is when somebody says, hey, I'm ready, you always need to check before you believe them. And so that's essentially just an extra step that you need to take within a condition variable. So what do I have here? Sometimes a wait function will exit before it's ready. So you should always check the condition is now true before you exit. So pretty commonly, you'll see an implementation like this, where we have cv.wait on the locker, which is our unique lock with a mutex. And then basically we have a little lambda function here where we're just going to return if the queue is not empty. So this is going to wait until the locker is available and the queue is not empty. If we get a wake up, let me make that smaller. If we get a wake up and the queue is empty, then we're going to go back to waiting because it's not ready yet. Okay, and then finally we have the semaphore. So a semaphore is like a mutex, or sorry, it's like a condition variable, which again, you know, it makes use of this mutex, but it's actually more than that. It's a CV with a count is how I like to think of it, and it's a signaling mechanism. So you could say to people, you know, I'm done, you can carry on. So the idea here is that the semaphore can count up with respect to how many different I don't know what the name for that would be, but this count, this value can be incremented, and that represents how many times it needs to be signaled before it goes down, and then you can access this resource. So if it's just counting up to 1, then that's essentially exactly what a mutex does, right? A mutex is just, is it locked or is it not locked? And so a semaphore, if it just counts up to 1, then, you know, that's the same thing to say locked or not locked, a binary state. But if a semaphore has a count that's 2, it could be locked by 1, locked by 2, or locked by none. And so suddenly now it's more than just a mutex. So a thread that is waiting on a semaphore can be signaled by another thread, which is an important note because that is not the case for the mutex we mentioned earlier. Additionally, counting semaphores are integer value semaphores, while binary semaphores are restricted to a value of 0 to 1. Again, this is where we get into the mutex territory. Semaphores are implemented by basically combining what we just talked about, the CV and the mutex. So they have this wait functionality where you're waiting for it to be free, and you also have the mutex under the hood, which is controlling the lock. So an example to kind of pin this all down is, let's say we have a soda machine, and I think I found this example on Stack Overflow, but I found it really helpful. And I do need more examples here just to conceptualize this because I understand it's a lot of stuff to take in at once. But the example here is we have a soda machine where the vendor will call up to add soda and is notified if the soda count hits 0. So the buyers will call down to take soda and will wait when they try to go down, but it's already 0. Okay, so the principle there is that we would need to have a semaphore here because you might have more than one soda can in the machine. And we don't want to call the delivery guy or the refill method until we run out of soda cans, until we reach 0. So the idea here is that you're going to call up, 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 which is going to increment the semaphore to have maybe 3 or 4 cans inside. And then as these buyers are coming in, they're going to call down, and they're going to wait when it's 0. And they're waiting essentially for, in this case, the queue to not be empty, for there to be soda cans for them to get. Okay, so I'm currently working on adding more examples here. If you felt like any of that was unclear, or you have an idea of what could be a better example for me to explore these topics, please let me know in the comments. I'm constantly trying to make this guide better and easier for me to understand, as well as, provide a better resource for you. So if you enjoyed this, please leave a like, and I will see you in the next section where we'll go into much greater depth on atomicity. Thanks.